In this video, we're going to be discussing the concepts of internal and external forces. Why are we doing this? Because even though both internal and external forces are both forces, they do affect systems very differently, and these forces have different kinds of properties when dealing with a system. And when we have to compact the system into a simple object, if we can identify which forces are internal or external, it will make that process much easier because, again, they have different properties that we can use and exploit to make our lives a lot easier. Also, there will be several times where we are going to be looking at a system that has a lot of different forces acting both on and in it, and we'll have to predict what the behavior is going to be. By simply identifying forces as internal or external makes this a much easier process on making a proper prediction, rather than trying to deal with all the forces that we're going to be overwhelmed with. In this video, we're going to identify the terms of internal and external forces. We're going to look at the roles that each type of force has on a system. We'll also look at how to simplify a system into an object. We're also going to look to see at how some of Newton's laws apply to internal and external forces. But before we do that, we need to review real quick what an object in a system is. So again, an object is a simple concept that we have. They don't really exist, but it's an oversimplification of a bunch of different things where we can view the group as one single entity that has no interior, and it's really simplistic to work with. If I make the statement that atoms are the building blocks of molecules, I'm describing a molecule as a system of atoms, but the atoms are objects because nothing's making up the atoms. We know there are things that make up the atom. However, I'm not considering them at this time, as right now the atoms are just the building blocks, so the atoms are the objects within the system of a molecule. However, a system, again, is a group of objects or even smaller systems that interact and affect one another. We often are using a system point of view when we're looking at what's happening inside the group because an object doesn't have an inside, so we can't ever consider what's going on because we ignore it. However, when we view this as an object, as a system, then we can consider what's going on the interior because we recognize it has one. So if I make the statement that atoms are composed of two parts, a positively charged nucleus and a negatively charged electron cloud, I am now describing the atom as a system of two objects, an electron cloud that is negative and a positive nucleus. Please notice that the nucleus itself is actually really a system. It's going to be a system of protons and neutrons, but I'm not considering that at this point. At this stage in the game, I'm describing an atom as two parts, a nucleus and an electron cloud. And so there are only two parts to the atom because, again, that's what I'm choosing to view it as at this point. The system that you choose to look at is purely arbitrary. So you always try to pick the system that's going to work the best for you. Internal forces are forces that act not only on a system, but the forces that are internal are all created by objects that are inside the system. So if I take a look at the forces that the nucleus exerts on the electrons, so here I have a force that's going to be pulling down on the electrons, pulling them to the nucleus of the atom because of the electrical forces, since the nucleus is positive and the electrons are negative. These forces are all internal forces, not because they're pulling into the nucleus, towards the nucleus that has nothing to do with it, not because they're pulling on electrons that are inside the system that has nothing to do with it. It is only because the forces that are on the electrons are actually coming from the nucleus, and the nucleus is part of my atom system. Because again, my system right now is just a positive nucleus and a negative electron cloud. So since the nucleus is pulling on the electrons, this force is an internal force because the source of the force is inside the system. Now, there's also forces on the nucleus that are being pulled by the electrons. And so the nucleus is actually being pulled out towards each one of the electrons. And these forces also are internal. Please notice these forces are pointing away from the system. They're pointing outward, but that has nothing to do with whether the force is internal or external. This force is internal simply because the electrons are creating this force, and the electrons are inside the system. So, so what determines you as an internal force is simply the thing that creates that force. If the thing that creates that force is inside my system, that force, no matter what, is an internal force. External forces, then, are forces that not only act on my system, but they are created by something that's outside the system. So the force of gravity that the Earth is pulling on this entire atom is an external force because the Earth is not part of my nucleus nor my electron cloud. If I have some other atom off to the side, and this atom is exerting some electrical force on this atom, causing some kind of bonding, then that would be an external force because this atom here is not part of this atom system. So the thing that determines if you're an external force or not is the source of the force, just like with internal. But for external, the source of the force is something that's not part of my system. When we take a look at chemistry, we learn a whole bunch of different processes and types of bondings, and one of the bonds we're going to look at real fast is the ionic bond. Now, for those of you guys who don't like chemistry, don't worry, this is not a chemistry course. We're just using this as an example. One of the reasons people have struggled with chemistry is because chemistry is very abstract. We are dealing with atoms and electrons and nuclei and things that are so small we have never seen them. We don't have any equipment to actually see what an atom truly looks like or what an electron looks like. And so people struggle with the examples that are shown because they're often oversimplified. And if you're not able to make the leap from the model to the real world, you really have a hard time grasping what's going on. I know I was one of those people. However, we'll be able to use the concepts that we've learned about objects and systems along with internal and external forces to actually see in how this type of process makes a little bit more sense. So if you remember about ionic bonds, if we have something, let's say, like sodium, which is Na, and chlorine, which is Cl, they're two neutral atoms, and when the atoms come close to each other, it is entirely possible for there to be a bonding that takes place. And it's called an ionic bond because all of a sudden these two atoms become charged. The sodium becomes a positive ion, the chlorine becomes a negative ion, and because they're positive and negative now, positive and negatively charged, oppositely charged, they will attract one another and they stick together. And so why does this happen? That doesn't make sense because all I saw was a neutral atom and a neutral atom. Why all of a sudden would they become charged? And we say, well, if we take a look what's going on, there are electrons that take place inside the atom's electron cloud. And that cloud, of course, orbits the nucleus. And if the atom is neutral, then the charge of the nucleus and the charge of the clouds are actually balanced. So the sodium atom has a nucleus that has 11 protons, so it has a charge of positive 11e, which is the fundamental charge. So there's a charge of negative 11 in the cloud. So I have 11 electrons out in the cloud. So I have a net charge of 0 for the atom. And for chlorine, I have 17 protons, so I have 17 electrons for the atom to be neutral. And so if I'm looking at this, it doesn't make a whole lot of sense on why all of a sudden there would be this charging change. And in chemistry, a lot of times what they like to say is, well, your electrons want to be in complete levels. And so if we take a look at the sodium atom, we have this one electron out here in this orbital all by its lonesome. And the atom would be very happy to get rid of that electron. Why? Well, we don't really talk about that, but we're about to see why. And here we have a chlorine atom, and well, it is almost completely filled. It's got one open slot right here that it could take an electron. So even though the atoms want to be neutral, they also want to have complete levels. And so the sodium, when it comes across the chlorine, says, hey, I'll be willing to give you this guy off my hands. And the chlorine says, hey, I'll be willing to take him. So the electron jumps over, and now my atoms are no longer balanced. Now all of a sudden I have a positive charge of 1e for the sodium and a negative 1e for the chlorine. So now there's an electrical force between these two atoms that are outside of each atom. I have an external force now because the force acting on this atom comes from this guy. So I have an external force on the sodium pulling it to chlorine. And likewise, the chlorine is being pulled by the sodium, which is an external force on the chlorine atom. And so they get pulled together and they stick together. Of course, these forces are internal forces of the sodium chlorine system, but they are external forces of just the sodium atom or the chlorine atom. Now, why does this entire process take place? To explain that, we're going to take a slightly different perspective than what you might have heard in chemistry class about atoms wanting to have complete energy levels or orbitals. We're going to look at this from a concept of internal and external forces. The nucleus is trying to pull all the electrons in towards itself. And so what happens is here we have a nucleus that has an attraction of 11 protons, and here I have 10 electrons that are orbiting it. They are much closer to the nucleus than this one electron right out here. Now, these electrons are not only the electrons that are inside this square are not only attracted to the nucleus, but they're also trying to repel any electron that is further away. And so this outsider electron is being attracted by 11 protons, but being repelled by 10 electrons. That means there's going to be a weak attracting force that's proportional to only one proton. If we take a look at the chlorine, what it's offering is a nucleus of 17 electrons. Oh, sorry, it's offering a nucleus of 17 protons, which is a larger draw than the sodium atom. Also, if we take a look at the number of electrons that are in the closer orbitals, they also have only 10 electrons. So at this point here in the sodium atom, I have an attraction of one proton. Here in my chlorine atom, I'm going to have 17 minus 10, which is 7 protons. So this is a much more attractive spot because I get to be influenced by 7 protons rather than only 1 proton. And so the electron will want to, of course, move over because it is not only being attracted by the nucleus, but it's also being repelled. And here I have a weak attraction with the nucleus and a fairly strong repulsion. Over in the chlorine section, I have a equal amount of repulsion, but I also have a stronger attraction. And so by looking at this as internal forces, it makes a little bit more sense on why this electron would want to jump ship and leave the sodium atom for the chlorine atom. You can almost think of it kind of like people who are going to a concert, and you have a choice on which concert you'd like to go to. We've got concert sodium, where I have a small stage and a small group, and you're going to sit in the back seat, and people are going to be in your way. Or you can have the exact same seat with the exact same number of people in your way, but the stage is going to be much bigger and the show is going to be so much louder and you're going to have so much more special effects. You know what? The seating might be the same, but the view is still going to be a lot better just because the thing I'm really attracted to is going to be just more. And so, again, when we look at this from an internal force perspective, it kind of makes more sense on why this ionic bonding takes place. So again, now we have our two atoms with the electron that has shifted over to the chlorine side. I can now see that I am no longer balanced. And so I can now see I have a positive atom and a negative atom. And so again, a lot of times, since we're not interested in what's going on inside the atom, really, look, I got a sodium ion and a chlorine ion, and they're going to attract and bond. We often just draw circles with the to illustrate the atom. We have their symbols inside there, plus and minus signs to show that they're ionized, and then we can just have them come together. Please notice here I'm viewing the atom as purely an object. I don't see a nucleus, I don't see electrons, they're nothing more than just the building blocks that form the sodium chloride molecule. When dealing with physics, we're going to often be working with Newton's laws of motion, and there are three laws that you guys have seen in earlier classes, and or courses, I should say, and we're going to look at two of them today. The first one that we're looking at is called Newton's second law of motion. Most of you guys have probably seen it overly simplified in your earlier courses, where it's been written F equals ma, where force is equal to mass times acceleration. And I have to point out that right away that this is actually incorrect because it's an oversimplification. This equation, F equals ma, is under the following assumptions. The first assumption is that you only have one force acting on one object. And in reality, we often have a system which is multiple objects, and we'll often have many forces acting on that system, or simplified object. And so the correct equation actually is net force equals ma. This funky little math symbol that looks almost like an E is actually a summation symbol, and it means that the sum of. So the sum of all external forces equals mass times acceleration. And that's actually what Newton's second law says, that the net or total external force acting on a system or an object is equal to the mass of that system or object times its acceleration. And that's the acceleration caused by the net force. And so this is a much more exact definition. This is what we're going to be working with. And you don't want to shortcut your definitions. You need to make sure that you understand what they are in full. Most cases where people struggle on physical concepts is not because the stuff is hard, but because they don't really understand what they're working with because they have learned shortcuts improperly before. So make sure you're working with a full definition and your life is going to be a whole lot easier. Please notice, though, when I'm looking at internal forces, they don't apply here. Internal forces never affect the motion of a system. Yes, the forces that are internal will play important roles. However, they do not actually affect the actual behavior of the system as it moves as a whole. So let's take a look at this scenario where I have a person who is pulling a 5 kilogram block, which is attached to a 10 kilogram block by way of a string. The blocks are on a smooth surface. The person is exerting 30 newtons of force. And my question right now is this 30 newton force an internal or external force? And to be very honest with you, if you think you have an answer, you are missing something. And if you're very confused by this question, then that's actually really good. And the reason for that is this is a very bad question. And the reason for that is because for me to answer this question, I need to know something, such as what are we trying to find out? What are we trying to solve for? And based on that, I will have to then be able to define what my system is. This 30 newton force could be an external force if my system is small, and it could be an internal force if my system is large. It all depends on what's going to be involved in what I'm looking for. So we're going to clarify the question slightly and say we're going to find the acceleration of the blocks and the string. Well, since I'm looking at the acceleration of just the blocks and the string, the person really isn't going to be that important. They're not going to be part of what I'm looking at. So the person was important in that they provided 30 newtons that's going to affect the things I care about. And I only care about the block and the string. or as to say the blocks in the string. So that means the person is not going to be part of my system. And since the blocks are not part of this, sorry, since the person is not part of the system and they're what created a 30 Newton force, this 30 Newton force is an external force. Yes, it acts on a 5 kilogram block that is part of my system. However, the thing that's creating the force, the person, is not part of that system. Please notice I'm naming my system as the 10 kilogram string and 5 kilogram system. This, if you are not my 10 kilogram block, my string, or my 5 kilogram block, you are not part of my system. So if you are creating a force that's going to affect the blocks or the string, and you are not the 10 kilogram block or the 5 kilogram block or the string, then your force is automatically an external force on my system, which means it has the ability to possibly affect my motion or the motion of this system. So, if I think of all the possible forces that are going to be acting on the system that are external, I actually have the 30 newtons from the person. I have the force of gravity that's coming from the earth pulling down on each of the blocks. And I have the force of the floor pushing up on each of the blocks. That's where the blocks are and falling. All of these forces are external because, again, the source of each of these forces is from outside my system. The force of gravity pulling down the blocks does not come from the blocks. It comes from the earth itself pulling those blocks downward. The force of the floor pushing up on the blocks is not from the blocks, it's from the floor. So that's pushing upwards. So all of these forces are in fact external. And none of these forces have to equal each other. Sometimes they do, and many times they don't. In this particular case, since the blocks are going to be moving across the flat floor, the force of gravity pulling down on the block and the force of the floor pushing up from the floor are actually going to be equal in magnitudes. That's because the block's going to be moving in a straight line. However, these forces don't have to be. If you've ever dealt with anyone who has walked in an attic, sometimes when you put your foot on the floor isn't strong enough to support your weight and you fall through the ceiling, or from your perspective, the floor. And that's because the force of gravity is much greater than the force of the floor supporting your body weight. So these two forces do not always have to be equal. And that's because they are external forces coming from two totally different things. Sometimes they are equal. Many cases we'll see the force of the floor and gravity being balanced out. But in cases on when something is falling or being lifted or something's being thrown or something is sinking, these forces will not be balanced. So you just have to be careful of that mindset that we often see because most people think that these two forces have to be equal, and they very rarely are. Now, in order to find the acceleration of the system, I am going to have to work with Newton's second law, which says that the net force on the system is equal to the mass of my system times the acceleration. So instead of dealing with a 5 kilogram block and a 10 kilogram block, I can very easily simplify my system down to a 15 kilogram block. Because if I was a person that was blindfolded and I was trying to pull the 5 kilogram block and the 10 kilogram block, it would be just as hard or just as easy as if I was pulling a single 15 kilogram block. So this is my system up on top, and now I have simplified it to an object down below. Please notice I have all my external forces. Now, I do have one minor change on my forces, how I'm going to have these labeled here, and that is if I take a look at the forces at the very top, I'm going to try and say here force of gravity on 10 kilograms, force floor on 10 kilograms, force gravity on 5 kilograms, and force floor on 5 kilograms. When I look at my object, I'm going to turn around and say force gravity on 15 kilograms because those two gravities have added up together. And the force of the floor will be on 15 kilograms because those two forces pushing upward will have to combine up to support the total combined mass. Please notice the 30 newtons is still 30 newtons because that was independent of these other forces. That's what the person was doing, and that's not changing. So I can very easily find my acceleration right now, which mathematically would be 30 divided by 15, so that would be 2. And the units for acceleration are meters per second squared, and we'll get more into that later on. So if you're not catching why that's 2 meters per second squared, don't sweat it right now. Just trust me, it is. And we're going to look into that in the upcoming days and weeks. But let's say I was looking for something else. Instead of trying to find the acceleration of the system, I was told that the string that was holding the system together could handle 50 newtons of force. If the string has to pull more than 50 newtons of force, it's going to break. So my question is the string strong enough to actually make the system work? Because, that's the thing. We're on the assumption that this string is going to be strong enough so that these blocks are going to move. And in reality, a lot of times we think something's going to work and it doesn't because something was just too weak. Well, if I look at my object perspective, I'm in serious trouble. And that's because, as far as the object is concerned, there's no string because there's no interior. I've got 15 kilograms moving at 2 meters per second squared, and that's it. So I cannot use my object perspective for finding this tension inside the string in this case because objects never have an interior. So anytime I'm looking for something that's going to take place inside my system, I need to look at the system as a whole. So once I view this now back as a system, I now have a string that I can now analyze. So I am not going to use the object perspective. However, I will probably use that as a starting point, and you'll see why in just a few moments. So I'm going to define my system yet again as the blocks and the string. The person is external. And since I'm looking for the strength that the string needs to have, I don't need to really worry about the person because, again, the person's not inside my system and the string is. I now have to recognize that the string pulls on both blocks. The 10 kilogram block is going to be pulled forward not by the person. The person's not touching the 10 kilogram block. They're touching the 5. But the string is touching the 10. So the string pulls the 10 kilogram block forward. And it's not because of the person, it's the 5 kilogram block that's causing the string to pull. That is what the string is touching. It's touching the 10 and the 5 kilogram block. So the thing that's pulling the 10 kilogram block forward is the string because of the 5 kilogram block. So the string is the conduit of that force. So we're going to turn around and say the 10 kilogram block is being pulled by the 5 kilogram block, and then the 5 kilogram block is going to be pulled from backwards from the 10 kilogram block. So the tensions in the string, or the force in the strings, are actually going to be pulling in opposite directions. Now, this is a very important type of force because my internal forces always come in pairs. In fact, you might have learned about them in an earlier course known as an action-reaction pair. Maybe you did, maybe you haven't. If you haven't, that's okay. And this all comes from Newton's third law that we're going to look at in just a few moments. But my internal forces always come in pairs without exception, and they always point in opposite directions. Now, if I want to try and find the tension force in the wire, I can now view each block as its own separate system. That's going to be my key thing. So I've taken my large system of two strings, two blocks in a string, compacted into one large block to find the acceleration. I am now expanding back out and I'm going to break my system up into now several small objects that are all interacting with each other. The tension force in the wire now has just become an external force for my two new systems because now my system is a 10 kilogram block and I have another system that's a 5 kilogram block. The wire is not part of that system. Not only that, but the 10 kilogram block is being pulled by the 5 kilogram block, which is not part of the 10 kilogram block system because it's only the 10 kilogram block. Likewise, the 5 kilogram block is being pulled by the 10 kilogram block, and that 10 kilogram block is not part of the 5 kilogram block system. So since they are two totally different systems, All of these forces are now external. I can now go ahead and find the tension force in the wires because I have the acceleration. So by simplifying everything into an object right away, I can find the acceleration, which allows me to now do this next step very easily. Because if I am looking at just the 10 kilogram block for a moment, I can say the net force on the 10 kilogram block is equal to its mass of 10 times the acceleration of 2 meters per second squared. So the tension force in that wire is 20 newtons. Easy enough. And ignore all this over here. That is something that is totally irrelevant. Don't even worry about that. You'll see why in just a few moments. So right away, actually, if we were told that the maximum tension that the string can handle was 15 newtons, right away we can see that this system actually will not work because the string will snap and uh, it will not actually function as we would expect it to do on paper. Now, if I take a look at the 5 kilogram block only, I see something that's kind of interesting. So I'm going to ignore the 10 kilogram block. Here I have my net force, which is the 30 newtons plus the force of the 10 kilogram block pulling back on the block. That's going to have to equal the mass of 5 kilograms times the acceleration of 2, which I found before viewing the whole system as an object. And I solve for the tension here. I find that the force on the wire is negative 20 newtons. Now before, it was positive 20, and now it's negative 20. These two forces are equal in magnitude, both 20, but they are opposite in direction. That's why they're opposite signs. One is positive because it's going to the right, and one is negative because it's going to the left. Internal forces always do this. You will always see that they come in pairs. They will always be equal in magnitude or strength, and they will always be in opposite direction. And this is where Newton's third law comes into play. Newton's third law is all about internal forces for a system. Newton's third law has often been oversimplified as action-reaction. And do yourself a favor. If you say, oh yeah, I know action-reaction, do everything you can to forget it because it is going to mess you up completely. It is something that has been simplified down to just a cat's phrase that no one understands what it means. In fact, we'll even see on how we can use this action-reaction phrase to get everything wrong, so you don't want to ever use it. Newton's third law really just says that whenever one object pushes on something else, that thing that's being pushed, quote unquote, reacts by pushing back on the first guy with an equal amount of force but in the opposite direction. So if Bob pushes Tom to the right, Tom's body automatically will push him back to the left. So in our problem, when the 5 kilogram block causes the string to pull the 10 kilogram block to the right, the 10 kilogram block in reaction is going to cause the string to pull the 5 kilogram block to the left, equal in magnitude, but again in opposite directions. Newton's third law only deals with internal forces of a system. Please notice that for this to work, there must be two objects, the 10 and the 5. No one object ever feels an action-reaction pair. Newton's third law never works on a single object. And this is actually where that term action-reaction messes people up. Because a lot of times you've heard this in an earlier class where gravity is pushing down on the block and the block's pushing on the table, so the table reacts by pushing up. And so according to Newton's third law, these two forces have got to be equal. And I have to turn around and say right away, no, it does not have to be equal at all. It's nice when it is, but it does not have to be equal. These are not action-reaction pairs. They are acting on the same object. The force of gravity and the force of the floor are both external forces. There is an action-reaction pair. I'm just not looking at them right now because I'm not looking at the floor itself or the Earth. So you have to be very careful when we're looking at Newton's third law. You have to recognize it only deals with internal forces of a system. And if I can recognize what forces are internal and external, then I never fall prey to these third law questions because automatically I know, hey, if you're external, you don't need to equal anybody. And since you are internal, you must be equal and opposite to somebody. And that's going to be the other internal force right there. So that's going to be a good time saver for you and an easy way to solve many of these conceptual questions that really catch most people off guard. So then some people think that Newton's third law only works sometimes and all the time. And the truth is, it's a law, so it has to work all the time. So then what is the reaction to this 30 Newton force? What is the reaction of the force of gravity or the reaction of the floor? And well, we have to then expand what our system is going to be. That's our thing on this. So if I take a look at the 30 Newton force, for example, the truth of the matter is the person is going to be pulled back to the left. If they're pulling the system to the right, then the system is going to pull the person to the left with 30 newtons of force. If I'm not considering the person, then I don't recognize that reaction. So everything's going to be okay. It's not something I'm concerned with. But the moment I expand out, I can then see that that force is internal. The bottom line is the floor is pushing up because the block is pushing the floor down. So there really is a force on the floor that I'm not considering. And while gravity is pulling the block down, the block is actually trying to lift the core of the Earth up towards the surface. It's not doing a very good job, fortunately, but there's a reaction force there. But I'm not worried about the core of the Earth right now, the structure of the floor right now, or what's happening to the person. I'm only concerned with the blocks and the string. So I define this as my system, and now I don't have to worry about all of the reactions. And that makes my life easier. But there are going to be consequences for all the forces. The bottom line is we could view our system as the entire Earth, which means every single force acting on the Earth, coming from the Earth or within the atmosphere, are all internal forces that all cancel out. That's why as you're walking across the road, you don't actually alter the rotation of the Earth around itself because all those forces are internal. Likewise, the force of gravity from the sun does alter the Earth's movement. So we have our solar system, and the force of gravity from the sun is in fact an external force on the Earth, causing the Earth to move in a circle. However, the solar system isn't actually moving across the universe because of these forces between the sun and the planets. That's because all of the forces of gravity between each one of the planets and the sun are internal. It's not going to affect the solar system at all. But our solar system is in fact moving in a circle around a galaxy because of all the external forces that the galaxy exerts on our solar system, particularly the big black hole that we have in the center of our Milky Way galaxy that's causing everything to rotate around it. And if I want to, I can just view the entire universe as one giant system, but then that is so global a point of view that every single force is internal, every single force is canceling out, and to the best of our knowledge, our universe, not our galaxy, but our entire universe, isn't going anywhere. And so we often want to be less global when we look at our systems, and we narrow it down to just the core pieces of interest. So in this case, when I'm dealing with two blocks and a string being pulled across the table, I'm not going to view uh, the entire Milky Way galaxy or our solar system. I'm not even going to view the person. I'm going to just go ahead and view the two blocks and the string because that's all I need to worry about. Everything else is going to be inconsequential. It's not my concern. All right, so I hope this helps out. Again, if you are unclear on some of this stuff, that's totally okay. This is just an introductory for us to go into class and discuss things and clarify things for you. There are going to be a couple of questions on Canvas I'd like you to try out right now. And just like last time, It's just for me to get an idea of what you've gotten from this video and what you already know, so we don't have to bore you with things you already know, and we can focus on the stuff that you really need to learn.